Alright, welcome back. Today we have text problem 10-98 for lesson 27. And let's get straight into it. Alright, so as we read through this, we see, especially from the drawing, that we have some forces acting on a massive pulley. So we're going to have some rotation. And if there's forces and rotation, then there's going to be torque. And if we have forces and torque, then we're most certainly going to have some Newton's second law. Alright, okay, so that's good enough for the read step. Our draw step is done for us. We will get into drawing our free body diagrams during the solve step. Alright, so given is what we have shown. Now for our assumptions, we have to assume that we have massless ropes, otherwise we would have to take into account the mass of our rope here, and the fact that they are non-slipping ropes. That's to ensure that as we pull here, we get the same amount of displacement, angular displacement, to support the amount of linear displacement of our rope. We can't necessarily say no friction because we have to have perfect static friction along the rope, but we can say that we don't want any axial friction. So right here at the axle, we don't want any friction that would impose non-conservative work to be done, which would alter how much displacement we actually see. Okay, so we've made our assumptions. We now have to go into our task, and it asks for the rotational inertia of our pulley. As we go into the physics step, I forgot to mention at the beginning of the lesson that I want you all to take out your scratch piece of paper or a blank copy of the problem, and I want you all to pause the video, catch up to where I'm at, and then before you resume the video, I want you to write down the necessary physics equations we will need for this problem. So get to it, and I'll see you in a minute. Alright, welcome back. Hopefully your physics step looks pretty similar to mine. So first we have our Newton's second law for translation, which will help us figure out or analyze the motion of our block down here. And then we have Newton's second law for rotation, and that will help us analyze the motion of our pulley. And going into Newton's second law for rotation is the definition of torque. Torque is a vector, and we use it as the cross product between the distance to the axis of rotation to where the force is applied, crossed with the actual force itself. We can rewrite this cross product in terms of magnitudes, such that the magnitude of the cross product is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle between the vectors. I'm going to emphasize that because we will see as we draw our free body diagrams, it's going to help make our life a little easier when we're dealing with pulleys. Alright, so let's get into the solve step. First thing I want you to do is to draw the free body diagram for our block here. And then once you've done that, resume and we'll check it. Alright, so we only have two forces acting on our block here. We have the tension force in the rope acting on the block, and then the force due to gravity pulling down on the block. Notice that I anchored the force where it's actually applied on the object. So the tension force is acting on the surface of the block, the top surface, whereas the force due to gravity is acting on the center of mass. Where we anchor these forces is very important now that we're in the torque block. Now I want you to pause the video again. I want you to conduct a Newton's second law analysis on our block. And resume the video once you are complete. Alright, welcome back. So we've done our Newton's second law analysis. If you got what I got, then great job. If not, then let's take a minute to go through it. Alright, so according to my coordinate axes, anything pointing up is going to be positive, anything pointing down is going to be negative. So we can see right off the bat that we only have forces acting in the y direction. So I'm going to go straight to doing a Newton's second law in that direction. So I have the sum of our external forces in the y direction is equal to the mass of the block times the acceleration of our block in the y direction. Now in the y direction we have tension, which is pointing in the positive direction, and we have the weight force of our block pointing in the negative y direction. So we have negative mass of the block times the acceleration due to gravity. That's all equal to the mass of our block times its acceleration. Well, I have a feeling, a hunch, that we're going to need this equation in terms of tension, because as we get to Newton's second law for rotation on our pulley here, we're going to need the torque caused by the tension in the rope as part of that Newton's second law analysis. So I've done that. I have tension is equal to the mass of our block times its acceleration in the y direction plus the mass of our block times the acceleration due to gravity. I kept these separate because, again, I have a feeling that we're going to need to isolate this acceleration in the y direction because that's going to play into our angular acceleration of our rotating pulley. So I kept them separate. I'll identify this as equation 1, and we will begin substituting here shortly once we start doing Newton's second law on the pulley. So I'm going to go to the next page and resume the problem. Alright, now that we have analyzed the motion of our block and gotten as far as we can get with the information given, I want you now to do a free body diagram of the pulley itself. That means all forces acting on the pulley and all critical angles and dimensions. Alright, so I will see you in a minute. Alright, welcome back. So, step 1, isolate the body. Our body is this complex pulley. Step 2 is to apply all forces. So the forces we have acting on this pulley, we have the applied force up at the top, anchored at the top of our pulley. We have the tension on the outside of the inner pulley, pointing down. We have the weight force of the pulley acting at the axle, and because it's resting on an axle, that axle is pushing back up on the pulley. We don't know which direction it's being pulled. But it is pushing at some angle. And so we have the normal force here with some critical angle. Well, we haven't gotten there. That's step 4. Step 3 is to identify your coordinate system. So it should look like your coordinate system for the block. The only thing we've added is the sense of rotation. So anything rotating counterclockwise will be positive, and any force trying to rotate it clockwise will be negative. That's going to be important when we get into our Newton's second law analysis for Newton's second law for rotation analysis. Alright, now we can get into critical angles and dimensions. So we have 3 critical angles. First one is pretty evident, and that is the angle between our normal force and the vertical. It could be the angle between the normal force and the horizontal. Doesn't really matter. As we get into torque, it's going to be inconsequential. The other two critical angles are the angle between our applied force here and the position vector of our force from the center of mass, or from the axis of rotation, excuse me. So we have a 90-degree angle here, and the same applies to our tension force, which is acting on the outer rim of the inner hub, and that vector is 90 degrees from our position vector of the force with respect to the axis of rotation. So three critical angles here, here, and here. Now as we get into our critical dimensions, the position vector, which we more or less look at it as a distance from the axis of rotation to where our force is applied. Tension is a distance small r from the axis of rotation, and the applied force is a distance big R from the axis of rotation. So that covers all four steps of the free body diagram process. I want you all to pause again, and I want you all to go through a Newton's second law for rotation analysis on our pulley here. See you in a couple minutes. Alright, welcome back. So we have our result. I have the result down here in black, and in blue I have the work I did to support the result in black. Okay, so the first force we have applied to our pulley is the tension force. And so the torque created by the tension force is little r hat, or r vector, crossed with our tension vector. Now from our first page of this video, or from your PRC on the back, in the bottom left corner, we can rewrite the magnitude of our cross product as the product of our magnitude of our position vector of the force times the magnitude of our force times the sine of the angle between our vectors. Well, we can see from our free body diagram that our position vector of the force and our tension force are 90 degrees apart. And the sine of 90 degrees is 1. And so we can apply that down here as well. So the torque created by our next force, the applied force, is equal to big R vector crossed with our force, applied force vector. We rewrite that in terms of magnitudes and angles. Then we take a look at the torque created by our weight force. Because it is acting at the axis of rotation, there is zero torque created by that force, because the distance of the force from the axis of rotation is 0. The same can be said for the normal force. It is acting on the axis of rotation, so it does not create a torque. So the only two forces that create a torque on our pulley is our tension force and our applied force. So I have written in black the negative torque from our tension force added with the positive torque of our applied force. Now, the negative and the positive come from my coordinate axes. I said that anything trying to rotate the pulley in the counterclockwise direction is going to be positive, and anything trying to rotate the pulley in the clockwise direction will be negative. And so that's where the negative and positive sign come from. That's all equal to the rotational inertia of our pulley times the angular acceleration. So let's go to the next page, and first we will label this as equation 2, and we're going to put these together and try to pull out the rotational inertia of our pulley. Alright, welcome back. Okay, so next up, I want you all to pause the video again. I want you to combine equations 1 and 2 and let's take a look at what we have once we have simplified the problem as much as possible. Alright, that wasn't too bad. So if your answer looks like mine, then at the moment that's as good as it'll get. Now, we do know the radius of our inner hub, we know the mass of our block, we know the acceleration of our block going up, we know the acceleration due to gravity, we know the radius of our outer hub, we know the applied force, we don't know our rotational inertia of the pulley, and we don't really know, or we weren't given, the angular acceleration of the pulley. But there may be a way of connecting this linear acceleration to this rotational acceleration, or angular acceleration. So take a look at your PRC. Try to find an equation on there that relates our angular acceleration and a tangential acceleration. Alright, so here's the equation we are looking for. The tangential acceleration is equal to the angular acceleration times the distance from the axis of rotation to the point in question, or the tangential point. Now what we were given in the problem was the linear acceleration of our block upward. And that goes to the point right here tangential to our inner hub. So the angular acceleration of our inner hub is going to be equal to the angular acceleration of our outer hub, as you may remember from the demo we did in class with the magnets. And so alpha is equal to a sub t over little r, because that is the tangential acceleration we have at little r. So we can apply that to our Newton's second law for rotation analysis. Now we have an equation that we can manipulate algebraically to solve for our objective variable, the rotational inertia. So go ahead and pause the video. I want you to attempt to do it yourself, and then once you've done so, resume the video and see how you did. And here's our algebraic solution. So if you got this, then great job. If you didn't, take a moment and try to rework it and see if you can get it. So from this point, all you have to do is substitute in your given values, and you get the answer 1.6 kilogram meters squared. Alright, so this was a tough problem, but I went through it nice and deliberately so you can see how it works, how we do Newton's second law for rotation, applying our torques, and looking at the angle between our force vector and the position vector of that force with respect to the axis of rotation. Alright, that's all I got. I will see you in class.